Yeah, I think we can start now. So, welcome. So, the goal for today's class is going to be to understand the Higgs mechanism. Okay? So, let's recall quickly what we did last time. Okay. So, what we did last time is we talked about essentially internal degrees of freedom. So, we started by looking at the fermionic Lagrangian. We saw what it looked like. And then we said we want to write fermions that have some extra internal degrees of freedom, and we figured out how to write that. And then we basically may turn the symmetries between these internal degrees of freedom into local symmetries or gauge symmetries and translated our derivative into this covariant derivative, which essentially adds an extra term which makes sure that it absorbs the terms that are generated by this kind of symmetric transformation. Okay? So once you do that, you can basically get interaction terms between the fermions and gauge bosons. So these were the interaction terms. And you can now, because there are internal degrees of freedom, you can think of gauge bosons in terms of matrices as well. So if you write your gauge bosons in this matrix form, then what you can do is you can relate the gauge bosons and the internal components of the fermions using these interaction terms. So one toy model that we did was SU2, where you have up and down type fermions, and you have certain this kind of gauge boson pattern that emerges because you have the sigma matrices that multiply each of the gauge bosons. So that gives you this kind of a matrix. And that gives you essentially couplings between up and down type gauge bosons mediated by this up and down type fermions, mediated by a charged gauge boson. And the same kind of fermions up or down that is mediated by the gauge boson component that was on the diagonal. So here it was A3. Okay, so that was here. So this was a toy model, and we basically defined some linear combinations as W's to make it look like what we expect for our beta decays, weak interaction decays. So remember, our weak interaction decay is something like n goes to p plus e plus mu. So you have neutron that goes to a proton, electron, and neutrino. So we wanted to write down a toy model that could do something like that. So since you know you want to have a charge change, so neutron is chargeless, proton is single charged. So you need some sort of charged gauge boson to carry away the extra charge that then gets transmitted to the electron. So this is how you can do this. Okay. However, we saw that this model doesn't really have, so it has a chargeless gauge boson as well, but it doesn't correspond correctly to the photon, right? So the photon is massless and it doesn't couple to the neutron and the neutrino, so it doesn't work. So we know this toy model isn't right. So what we want to do now is to actually go to the real model, that the standard model that describes the universe, and that we call the standard model. Okay, so that is the goal of today. And to understand that, we have to understand something called the Higgs mechanism. Okay, so it's going to be a sort of longish story. And what the Higgs mechanism essentially does is it connects this vector boson sector with the scalar boson. Okay, so that is how you give masses to the vector bosons, and also have this peculiar property that we will see in just a minute. Okay. Okay. So okay. So this is the plan for this lecture. So we're going to start with the scalar Lagrangian. Okay. Then we're going to talk about Lagrangians for vector fields. Okay. We'll also talk about gauge transformations. for scalars. Then we'll talk about vector fields and mass terms for vector fields. And then we'll talk about what is called the abelian Higgs model. Yeah. Then, so abelian Higgs model is for U1 gauge bosons. Then we'll do the Higgs mechanism for SU2, which is still a toy model. And finally, we have Higgs mechanism for SU2 across U1, which is the true standard model feature. So it's sort of a longish story. It might take us a while to get to where we want to get to. Okay, so let's start. Yeah, just before I start writing down some questions, are there any questions so far or anything about last week's class? Okay. Okay, so you might have all seen this Lagrangian before. So if you have a complex field phi, then this is what the Lagrangian looks like. Right? And you can do your usual equation of motion, and that would give you this Klein-Gordon equation, right? Which is just the equivalent of or similarly P mu to m squared. Right? So that is our usual special relativity condition, and this is just translating that into the language of fields. Okay. So if you look at this Lagrangian here, one. So this one is invariant under phi going to e to the I alpha phi. So this is quite obvious. So phi star will get an e to the minus I alpha. So this term is going to be automatically invariant, and this term also similarly, especially if phi is not depending on x. Okay, so you just get the cancellation of e to the I alpha coming from phi and one coming from phi star, and the Lagrangian is invariant. So let's try to make it a local symmetry. So instead of alpha, we have alpha of x. Okay, so it depends on x. And then, as you know, what will happen? We'll go to term alpha is times phi. Right, so you have this extra term, and the way we usually absorb this extra term is by defining a covariant derivative in this way, where you have this extra field a mu, which transforms as a mu alpha. So this is the same as last time, right? So now if we look at what is happening to so this gives you a term that's as before. Then there is going to be a term that's proportional to del mu alpha. So you have a phi star coming from this guy, or rather del mu phi star coming from this guy, and just a phi here. So let me take this del mu alpha outside. So we have phi. Right? So you have two terms like this, and you will have a term that looks like. So we say if alpha is small, you can ignore terms of order alpha squared. So the last term we can ignore. Okay. So that gives us these two terms, and essentially what we want is something to absorb exactly this guy here, which we do not using this. Okay. So we have our current, which you define as star, so like this, and if you look at phi, just star. Okay, so if you can look at star 5, then that gives you the required first term. Then you have mu, star, and an extra term that looks like this. Okay, so this is just multiplying these two guys here. So the first term is quite obvious. The second term looks like a mu j mu, which is also as expected. J mu is the current, right? And then you have this extra term, which we don't yet know what to do, but keep an eye on this. So this will be important very soon. Okay. So let's just mark it. Okay. All right, so now let's go to the other sector. So let's look at Lagrangian for vector field. Okay. So I'm not sure you have studied this in detail in your field theory course. It usually happens in the second field theory course. So I'm just going to write this down, and I'm going to try to heuristically explain what this is. Okay? So the Lagrangian looks like this, okay, where f mu nu is defined in the following way. Okay? So if you remember your EM course, then you will probably have seen these equations before, right? So you have equations like this, and so on, right? So you have Maxwell's equations that you can derive from these. So you can do this as an exercise where you can, so your field is mu, so you can derive equations of motion. From this Lagrangian up here, okay? And what you will get is essentially the Klein-Gordon equation. It looks like this, okay? So this is for massless area. Okay, so this is what the Lagrangian looks like. I'm sorry, I'm sorry we can't do it in detail in this course, but then rederiving every field theory thing will sort of take us very off course. So I would suggest that we can just start from taking this as a well, not quite an action, but just as a starting point. I'll just tell you that this is the Lagrangian, and we go from there. Okay, and this is the formula for it. Okay, so another thing to note is that if your gauge transformation is this, then you see already that F mu nu is invariant under it. Right? Because you have del mu A nu minus del mu A nu. So the first term will give you del mu A nu plus del mu alpha. I'm sorry. Del mu alpha. And then you have del mu A nu minus del mu of del mu alpha. And since del mu and del nu commute, these last two terms will cancel out. Right? So you will just get F mu. So this tells you that this is an invariant quantity. Okay. So another thing we can do is generalize, use d mu. Okay. So remember d mu was del mu minus I d mu. And you can again look at d mu minus d mu. And in this case, you will get usual. And then there's right, these terms will cancel out and you have essentially the same thing as before. Okay, so let me define now F mu as this. Okay, so it's going to sound a bit opaque because we haven't derived these from first principles, but I'm just trying to make connections to before to show you that what we are doing is sort of sensible. Okay? So the reason we've generalized this del mu to d mu is to incorporate cases where you have extra internal degrees of freedom, which meant, if you remember, that your fermions look like you have this extra components here, and then you have generators A of these internal symmetries, and we therefore had del mu minus So this is how we had defined our covariant derivative in that case, where this is the matrix in the internal space. And these now you have extra gauge bosons corresponding to these internal symmetries. Right, so we want to basically generalize also our field tensor F mu nu. This is called the field tensor. In the same way. Okay. All right. All right. So let's look at what del mu nu looks like in this case. Okay. So we had del mu T, A. So everywhere where you have A, you write it as in the following way. So this is, you're separating out the space-time dependent part and the generator part. Okay? So we have minus I So this is what it would look like. And then if you do okay, so the first term looks as expected. Okay. For the second term, let me just copy down the first. The thing that we've written before. Okay. Then the opposite sign this. Okay. So then you have, remember you have a mu, right? So what I'm going to do is just should be a B. I'm just going to use the same A's and B's as they are in the previous terms, just to make things easier. Okay, so just looking at these two terms, that looks like right. So this, yes. You get a commutator, and usually for these groups, so if you remember for SU2, you have sigma I, sigma J is sin I, J, K, sigma K, right? So you have a relationship between the generators themselves in the form of this commutator. So to keep it general, instead of using this epsilon and sigma notation, the common notation is to use these F's, use this dA, dB, ABC, DC. So where F, A, B, C are like these epsilon matrices. Okay. So what that tells you, essentially, your step. This should be here. Sorry for the confusion. So let me write this in terms of C. DC. Okay, so this is what it looks like. So let's look at it again just to make sure we've understood. So the first two terms are obvious from just the derivative terms. Then you essentially have two matrices, one A mu and one A mu, and in this the second term the order is reversed. So there's a matrix for A mu and a matrix for A mu. Okay, And to make things easy when I pull out the space dependent parts, I've just named the summation indices the same for the nu and the mu. Okay? So when you do that, you see that you end up with this commutator, and a property of these symmetry groups like SU2, which we know well, is that you can write a commutation relation between the generators. And in general, you can write it in this form here. So if T and TB are generators, then their commutator is written in this form. In case of SU2, you know what exactly this FABC are the same as epsilons. Okay. So this is your formula for your F mu nu. Okay. And you can also write your F mu nu in that case as F mu nu A dA. So you can pull out the matrix component and the space-time component. And if you do that, let's again use C to make this easily visible. So it becomes a more complicated relation. And in particular, you will notice that there is a term where you have two gauge bosons already in the definition of this F mu nu. So when you write down the Lagrangian, which is the same as before, except now you also sum over the extra index that you have. Okay? So you sum over not only the space-time components, but also the internal symmetry components. So you can see already that when you do this multiplication, you will get a term that will look like this del mu A, and then you have again these two A nu terms that come from this guy here. And what that means is that you have results in self-interaction terms. Well, let's not call them self-interaction, but so you have interactions between 3 or 4 gauge bosons. Okay. So we'll come to this in detail when we talk about E plus E minus colliders and electroweak precision tests. But this is where these extra terms come from. Okay. So this one more thing to note before we can take a break and go to the Higgs mechanism has to do with the gauge coupling. Okay. So remember, we defined a charge for the fermion. Okay. So we had written our covariant derivative like this. So we can just extend it for extra degrees of freedom by adding generators. And if you remember, you have this extra gauge coupling, which is sort of the charge of the fermion when it couples to the gauge boson. So it turns out that this quantity, this gauge coupling, is actually quite fundamental, because when you have these extra internal degrees of freedom, because you have this extra term here. Okay?
Excuse me, ma'am.
Yeah.
Is this the same G as the as was discovered, not discovered, like calculated in the muon G2 experiment?
So that G is actually different. So that G has to do with the gyromagnetic factor. So that is something slightly different. That's not the same thing. No. It's just a coincidence that we use the same quantity.
Okay, thank you.
Yeah. Okay, so all right, so you remember we write the derivative like this, and if we calculate our f mu nu using this formula, so we just calculate the full f mu nu here. So let's just see what's going to happen, right? So I'm going to write it with a different color. Okay. So if you had a g here, okay, what that would mean is that every time you have this extra term, you would get a g, right? So you get a g here and a g here, which means you get a g here and a g here. Okay? So that corresponds to having a g here. Okay? So when you write it like this, you get a g term here, and even if you redefine your fields, so even if you redefine your a mu's to absorb this g, so let me call this prime, okay, then what happens is that your first term, let me rewrite this full formula first. Okay. So we had this. So in terms of a mu prime, what we get here is g c plus. So one of the g's get absorbed with one of the a mu's, and you have only one coming from the other one. G, B, C. That's just 1 by g times what you had earlier. Okay. And then if you write your Lagrangian, then that looks like g squared. Okay, so both of these notations are right. So you can either write it as minus 1 by 4 f mu nu, or 1 by g squared f mu nu prime, or well, without the primes. Either of these notations are right. The only thing to know is that the g is, in that case, hidden inside here. So it's inside the way you write f mu nu. Okay? And this is the notation that we will use to make it more explicit rather than redefining your a's and pulling your g outside. Okay? So I just wanted to show you this because some textbooks use one notation, some textbooks use the other notation. So just to avoid confusion. So the reason I was talking so much about this guy G is that it turns out that, so I told you that these extra terms here result in terms like this, right? So you have 3 gauge boson vertices. And what that will mean is that the interaction between these 3 guys will depend exactly on this coefficient G. So if you can observe boson processes. Means you can directly measure this guy G. Okay, so this is why it is important to remember, and an important differentiating factor between these non-abelian or non-commuting gauge groups like SUN and a commuting gauge group like U1. Okay, so when you had U1 in this case, even if you rewrite your F mu nu in terms of d mu, capital D mu, you still do not get this extra term which has these self interactions between gauge bosons, right? So you can always redefine your A mu by absorbing these coupling constants, and it will not come out as a fundamental quantity in that sense. Whereas here, this G is a fundamental coupling constant that becomes a property of the model that you're writing down. And you can actually measure its value using processes that depend on vertices like this. Okay. So I realize it was, if you have not done field theory before, it could have been very confusing. So if you have any questions, maybe you can answer them now.
Can you repeat the last sentence again?
This, the thing that is written in purple.
Yeah.
Okay. Okay. So the idea is this. Okay. So the idea is simply this. So when you write down your Lagrangian for these gauge bosons, what you have because of the fact that the generators of this group do not commute. So when your transformation was just exponent of a number, you could just commute it. But here, because it's an exponent of a matrix, you cannot commute the two matrices. So so whether you do one transformation first and then the second, or the second first and then the second and then the first, will make a difference. Okay, so that is encapsulated in the fact that these generators don't commute, and that then reflects in the way you define your field tensor. So the quantity that is then gauge invariant is not just del mu A mu minus del mu A mu, but this whole quantity with an extra term. So this is then your gauge invariant quantity. And because of this extra term, when you write down the Lagrangian, you get essentially terms that look like del mu A mu times F A B C is a G A mu A mu B D C. So you will get terms like this, which when you draw the Feynman diagram corresponding to it, look like this. Okay. So normally what you have is you just have, say, E plus E minus going to something else. So let's pick muons, mu plus mu minus. Okay. So this was when we dealt with fermions, but now you can have for SU2, for example, a case that looks like this. So you have E plus E minus that goes to, oh sorry. So this is again jumping the gun a bit, but we'll come to it. W plus W minus, and then this guy can be, can be the third component in the gauge. So let me just write it as Z, but we'll see what that is. Okay. So you can have extra things that look, extra terms that look like this. And if you can measure this process, then that gives you a handle on the coupling that is responsible for this. Okay, so you can measure this coupling. So it's no longer just a convenient normalization factor, but becomes a concrete observable that you can actually measure.
I'm here. The W plus W minus will further decay into some
Something else, yes. So normally, we can go back to our toy model here. So remember your W plus. So this part is good enough. It works. So for example, you can have a W that decays into an E and a neutrino. So it's a charged guy, right? So whatever it decays into, the final state will also have to be charged.
Okay.
Yeah. Okay, all right. So then we can continue with the Higgs mechanism. Okay. So there are two ingredients that we've sort of collected. So the first ingredient was when you operate your gauge or your covariant derivative on your scalar field, that gives you a term that looks like phi star phi, a mu, a mu. Okay, so this was one component. The second component we looked at was essentially that is how to write your Lagrangians for vector fields. Okay. Okay. So now the third thing that we need to do is how to write massive vector fields. Okay. So remember we had a mu goes to a mu plus del mu alpha. Okay. So if you have a term that looks like a mu, a nu, which would have been your traditional mass term, this will give you a mu plus terms of order alpha square, which you can ignore. But you still have these two extra terms, which means this term is not gauge invariant. Right? So we go back and we make this, we see that here this term gets, so a term proportional to a mu gets generated automatically from this kind of covariant derivative of phi. Okay, so we're going to try and use that to generate masses for our gauge bosons. Okay. Okay, so the general idea is this. Okay. So since we know that you can get a phi squared new kind of term from phi. Okay. So then what we want to do is, instead of this phi star phi, we want to give it a constant number. That will be the mass. So we want to somehow stabilize this phi star phi to one number. Okay, and the way to do this is to give a potential to the field phi. Okay, so this is the general idea. So if you have some extra potential field phi and it naturally comes to rest somewhere here, right? So this is some non-zero number. So let me just call it E. Then when you expand around this minimum, around the minimum of phi, then you will automatically get a V squared coming from each of the phi star phi, right? So that will automatically give a mass v square a mu kind of term. So this is the idea, and we'll put it into practice in a more rigorous way. Okay. Okay. So remember we had a phi, which is a complex field, and what we can do is we can sort of, so remember we have, if we have any z, we can write it as r e to the I theta. So we are doing the same kind of thing. So we are separating out the radial part and the angular part. Okay. So let me call this guy theta, which is also a function of x, and then this different phi, the variable var phi as it's called in LaTeX, can represent the radial component. So we know our transformation is phi goes to e to the I alpha phi, right, which is just a rotation, which simply means that it goes, so this guy doesn't change. What changes is just the exponent, and you can make a gauge choice. So this actually will also tell you what exactly does it mean to make a gauge choice, which is, so this transformation that we are making here is essentially completely user determined. Right? It's just telling you that you can pick a different alpha for each point in space time, right? So if you can write your field like this, you can make a gauge choice where your theta is always the opposite of whatever the gauge choice you're making. And if you do this, then your phi is just simply always. Okay, so you don't have to worry about the exponent. Okay? And your phi star phi in the term simply just becomes phi squared. So when I was talking about giving a potential for this phi here, so since we've gotten rid of the exponent part, we can essentially give a potential only to the radial part. Okay, and this looks like so. This is the common potential that is chosen. So let's draw. What does this look like? So this is what is called the Mexican hat potential. So because it sort of looks like a sombrero hat that you put on, and it has these two minima. So this is phi. This direction is p of phi. And you can check what the minima stands at. So you can do 0, that tells you minus 1 squared plus lambda phi. 0, which tells you either phi equals 0 or phi square root of square phi lambda. And this is what you define by v. So it has two, or rather 3 points where the first derivative is 0. It's easy to see where they are. So here you can draw a tangent and you see it's flat. So these are the two minima. And here also, if you draw a tangent, it's flat. So that's also an extremum, right? So to find which one is the minimum, you can do v by del square. You can look at that. Okay. So there is mu squared plus square, right? So at r equals 0, you have square root right of r squared is minus 1 squared. At b, you will have essentially squared equal to 2 squared. Okay, so you see that this guy is the minimum and this guy is the local maximum. Okay, so now that you figured out what the minimum is, you can essentially write your phi as v plus h. Okay, where now your h is the part that's dependent on x and p is just a constant number, which is called the vacuum expectation value. Or VE. Okay. So you are essentially expanding around the minimum. So your vacuum is always the minimum of your theory, right? So that's going to be your vacuum. And once you expand around that, you can write all your terms. So you can write, for example, your V of phi, which then looks like fourth. And you can also write your phi square term as so this gives you a v squared mu plus hv plus so the three terms. So there's a one term with a constant which becomes the mass term. Okay. And this guy, the second guy, looks like one Higgs. So the H is called the Higgs field. So one Higgs with two gauge bosons. And this last term is where you have two Higgses with two gauge bosons. Okay, so these are the three terms that result from this. Okay. So what we've achieved here essentially is this. So if your Lagrangian is this, okay, so and you can have also this. So if you write down Lagrangian like this will automatically result in massive gauge bosons. Okay. So this is the essence of the Higgs mechanism. You start with a scalar, you charge that scalar under a gauge group, so it has this local symmetry of this exponential transformation. And if you provide a potential for this scalar that is away from zero, a minimum that has a minimum away from zero, then that will automatically result in the gauge boson getting a mass. Okay, so this process of getting a vacuum expectation value other than zero is also called spontaneous symmetry breaking. And the reason it's called that is because your Lagrangian is explicitly invariant under gauge transformations. So there is nothing in this Lagrangian that breaks your gauge transformation symmetry. However, your vacuum is inherently unsymmetric, right? So it's not, so there zero would have been a symmetric vacuum, but plus or minus V is an unsymmetric position that you've chosen. So your ground state is not symmetric. However, your Lagrangian is still manifestly invariant under gauge symmetries. So that's why it's called spontaneous symmetry breaking. So any questions so far? Okay. So one more thing happens. So you have your A mu, which remember goes as A mu plus del mu alpha. So this is what we had all along, but now we've fixed the gauge, right? So this is nothing but del mu theta, where your theta was this theta component here in the field, right? And this is essentially what people refer to when they say swallowing a Goldstone boson. Okay, so this essentially corresponds to the longitudinal component. So remember, this theta component always comes with a del mu theta, so it's always parallel to the momentum p mu, right? So that's why it provides this longitudinal component to the gauge boson, and it's also called swallowing a Goldstone hole. So another thing to remember is that we did not add a potential in the theta direction. Okay. So the potential is always in the radial direction, not in the theta direction. Okay. So I don't see any questions immediately. So let me just recap. Okay. So this is what we did. We wrote down a Lagrangian that had a scalar component and a so right now our gauge boson does not have these extra internal degrees of freedom. So we just have just your normal U1 gauge boson, and by providing this gauge symmetry to the scalar and an extra potential in the radial direction, we automatically generated masses for our vector boson A. Okay, so now our next step is to generalize this for SU. For SUN. Okay. So we know your A mu becomes A mu A dA, or d mu becomes G. So, right, so these are things that we already know. So let's do this explicitly for SU2. Okay. So if you want to charge a scalar under SU2, so your scalar, which was just phi, is now also a two-component scalar. Okay, so it would have been phi u, phi d in our previous notation, up and down. And remember what we did here was we essentially separated out the radial and the exponent part, right? So we're going to do something similar here as well. So if you have any two component vector like this, you can essentially write it as, so you can, using this symmetry, you can essentially write your phi. This is doing the same thing that we did before, except now we are doing this for a two component guy. Okay, so what this is essentially telling you is that you can use polymatrices So these are your polymatrices as generators for any uh, transformation in SU2. So what this is essentially saying is that if you had U1, you would start with any point, any real number, and you could just multiply it by e to the I theta to take it anywhere else on the circle, right? So this is what you would do for U1. So you're doing something similar in SU2, which is you're starting with a real number on, so this you can also write it as, say, y1 plus I, y2 plus I. So there are multiple ways of writing the same thing. But what you're essentially saying is that you can start with something that looks like this, that just has one real component, and you can rotate in this SU2 sphere to get any other point on that sphere, just as long as you don't change the distance from the origin. Okay? So we're going to write our phi in this form here. Okay? And then essentially repeat. So similarly for. So we're going to repeat what we did before. Okay? So what we want to do is we want to write a del mu phi. Okay? And remember now in this case, we would have minus IG phi, right? And this guy we saw last time looks like this. Okay, so we're going to simplify a lot and not look at all the terms that come. So we want to look at del mu phi dagger, del mu phi, right? This is the term that we want to look at. So we can see already that multiplying the first terms will just give you the d mu phi kind of term. If you mix the two, where you have one d mu phi and one term like this, you still don't get the mass term, which should have two copies of the gauge boson, right? So the term that we want to look at is where you essentially pick out this term coming from both the derivatives. Okay? So let me just write down that term. Okay? So what we want to look at there, so this contains g squared. So there's an I and a minus I coming from the dagger. Okay? So you get a neuron sign here. And let's, okay. So we'll look at GP times phi. So this is the term that we want to look at. Okay, so this is the only term that we will look at in detail. So let's simplify our value phi term a bit more. Okay? So the first thing we did was we wrote phi as theta A times 0 and phi. Okay. Okay. And we can, second thing you can do is you can choose a gauge transformation. Right, so we had phi goes to e to the I alpha A tau A phi. This was our gauge transformation. And we've written phi in this form, which means you can always again choose your theta A as minus alpha A, same as before. Which means that in this gauge, choose a gauge, actually not a gauge transformation, choose a gauge. So in this gauge, essentially you have your phi is simply 0 and phi. Okay? So in this very simplified gauge, we can write down what our that looks like. So that looks like phi. So let me put this in heights here. Now your sigma are Pauli matrices, right? So these are the generators. So I'll take the two outside. Right, this is what it looks like. So again, let's just look at this term here. Okay. And also recall you had your phi, which we wrote as p plus h, right? So just looking at this part of the term, so you have minus h. So 3 times phi, which I'm going to write as p plus h. And this, oops, that's the bottom. This is W1, it's W2, this one plus h, and the bottom one is W3, is V plus h. Okay, so these are the terms that you get. And for the master, we only want to look at proportional to V. Okay, so we don't worry about h right now. So that gives you this. You can take an overall view outside. Okay, so this is what it looks like. And the mass term will come from right? So just this term transposed and taken the complex conjugate of. Okay. So that gives you 4. right? Which means this is G squared by 4. Two, two, plus three, three. Okay. So what this is doing is it is giving you 3 gauge bosons, all of them having the same mass, given by this. Okay. You can also try and redefine your W plus minus gauge bosons as before. So what you can do is two. Okay. In which case you get GB squared by 2 plus W minus, and you get G squared by 4 W3 W3. So you can also redefine your W plus minus as before, and this is what you get. All right. So what this is telling you is you have 3 massive gauge bosons. Right. However, our original question remains, where is the photon? Which, as we know, is massless. So we know that even though you can have your W plus minus in this way, you still don't get a massless photon from this theory. So we need to still modify this to add a massless gauge boson. And so we want to do SU2 cross U1, which means that your scalar field now not only has SU2 charges but also U1 charges. Okay, so we're going to do a combined combination of both. Okay, so what would your covariant derivative look like? So you have del mu as before, G W tau A as before, and then you also add an extra term corresponding to the U1 gauge field. Okay. So you can again write your matrix as before. So let me do some redefinition. Okay, let me write this. So since your tau A is sigma A by 2, so to make things look nicer, what I'm going to do is I'm just going to write a divided by 2 here. Okay. So that we can take 1 by 2 outside. So it's just a redefining of what your G prime is. So you have 1 by 2 outside, there's an I. So you would have a G times W3 and minus G times W3 as before. Okay. Then you would have a W1 minus I W2 and W1 plus I W2 as before. So remember here there is a hidden 2 cross 2 identity. So you have a G prime B that appears on the diagonal. Okay? So this is what your matrix corresponding to the gauge bosons looks like. Okay? And so remember now again for the mass term. So let me call this something. Let me call this guy capital M. Okay. So your mass term essentially came from your M multiplying 0 V, right? So let's look at what that looks like. So there you have I by 2, essentially just, so this, the V times M. Oh God, okay, that's not right. V times 7. So in the first case, you only get W1 minus I, W2. In the second case, you get minus G W3 plus G3. Okay. So it's what we did here, right? So this is the only thing that survives when you multiply it with 0, when you multiply it with a vector of this form. These are the only things that survive. So that's what I've written down here, except now you have this extra term that comes from this extra term that we added. Okay. Right. So now we have 4 gauge fields. So we have W1, W2, W3, and B. And what we can do is we can define physical fields W plus minus as before. And you also define two new fields which we name A and Z. So these all have a mu here in the following way. So it's just a rotation of the earlier fields that you had, B mu and W3 mu that were on the diagonal. And we write them in terms of these new physical fields. Okay. This theta is often also denoted by theta W and is called the Weinberg angle. And you have sine theta, which is given as plus theta. Okay. So you can just write this out. What this simply means is your W3 mu is sine theta mu is cos theta. So mu is cos theta mu minus sine theta 7. Okay. Another thing to notice here is that there's only one combination of this W3 and B that survived and came with the V, right? So when we do, so what we get essentially is this, right? 0, B, 0, B. So these are our mass terms. Times 0, B is given by this. Okay. So when we do this, you notice that there's only this one combination that survives, and the other so this is corresponding to this guy here, whereas the combination corresponding to this guy here does not actually come with a V at all. Okay, so that corresponds to having no mass or a massless gauge boson. So there's going to be one combination that comes from this that has a mass, and one combination that doesn't have a mass. Okay, so I'm going to give this as an exercise just to figure out masses of W, Z, and A, and we will check this in next class. Okay. So please do this before you come next time, so that we have some base for going forward. Okay, so I'll stop here for today. So let me just recap the last part. So what we did in the last part was we said that just using simple SU2, we get 3 massive gauge bosons, but we still don't have a photon. So we added one more gauge transformation, a U1 gauge transformation, and changed our covariant derivative accordingly. That changes our mass terms essentially, because you get an extra contribution from this new gauge boson also in the mass term. And we looked at what the new mass terms look like, and we see that you still only have 3 massive gauge bosons, the W plus minus as before, and one combination of the W3 and B. And this particular combination can be got from the original W3 and B by using a simple rotation, and this angle of rotation is called the Weinberg angle. Okay. So that is where we stop for today. So any questions so far? So this is by far probably the most complicated class that we have. I think everything else in this course is simpler than what we did today. But I wanted to do this just to give a base of what the Higgs mechanism is, and what kind of, to understand what kind of gauge terms come as a result, because otherwise it gets very hard to go into the details of the collider physics that we need. Okay, so yeah, I'll stop here, and I'll just stay online for any questions, but feel free to leave.